Hey there, AB engineers. Welcome to AB Engineering Guild, your hub for agricultural and biosystems engineering. In this video, we're diving into a really important topic from the Philippine Agricultural Engineering Standards, also known as Paes. Today's topic, Paes 218, 2017, Open Channels Design of Main Canals, Laterals, and Farm Ditches. Sounds technical? Don't worry, we'll break it down into simple, easy-to-digest parts. Let's go. So, what exactly is Paes 218:2017? This standard provides guidelines for designing open channels used in irrigation systems, that means main canals, laterals, and farm ditches. These channels are responsible for distributing water efficiently from the source all the way to the crops. Whether you're designing for a big irrigation project or small-scale farm, following this standard ensures proper water flow, minimal losses, and efficient use of resources. Before we dive deeper into the technical side of Paes 218:2017, let's take a quick look at how this standard came to be, and why it's important for agricultural and biosystems engineers like us. The formulation of this national standard was initiated by the Agricultural Machinery Testing and Evaluation Center, or AMTEC. This was part of a project called Enhancement of Nutrient and Water Use Efficiency through Standardization of Engineering Support Systems for Precision Farming. Sounds like a mouthful, right? But in simple terms, this project aimed to create better systems to help farmers use water and nutrients more efficiently, thanks to precision farming and engineering support. The project was funded by PCAARRDDOST, that's the Philippine Council for Agriculture, Aquatic and Natural Resources Research and Development, under the Department of Science and Technology. Now, let's talk about the legal foundation of this standard. Under Republic Act 10601, also known as the Agricultural and Fisheries Mechanization Law or AFMEC Law of 2013, the Bureau of Agriculture and Fisheries Standards, or BAFS, is mandated to develop technical standards and procedures for agricultural and fisheries machinery. So, in line with this mandate, BAFS developed and endorsed this standard, but before it became official, it was reviewed and approved by 1. The Department of Agriculture Secretary, 2. Through the Bureau of Agricultural and Fisheries Engineering or BAFE, and submitted to the Bureau of Philippine Standards or BPS, for final numbering and official inclusion in the Philippine National Standard, or PNS, repository. And just so you know, it's not just any kind of document. Paes 218:2017 was technically prepared based on the BPS Directives Part 3:2003, which are rules for how international standards should be structured and drafted. That means it's been carefully written to align with global standardization practices. Now here's a little tip on terminology when reading the standard. 1. When the word shall is used, it means the requirement is mandatory. You must follow it. 2. When the word should is used, it's a recommendation, something advised or preferred, but not absolutely required. So, there you have it. Understanding the background of Paes 218:2017 helps us appreciate how much effort goes into creating national standards, and how they support the goals of mechanized, efficient, and sustainable agriculture in the Philippines. Scope. This standard provides minimum requirements and criteria for hydraulic evaluation and stable design of open channels specifically for main canals, laterals, sublaterals, and farm ditches assuming uniform and steady flow. Symbols and nomenclature. Here are some symbols that you might encounter while learning this subject. Take note of these as they are important in knowing the definition, discussing equations, and solving some problems. Feel free to pause if you want to jot down those terms. Definition of terms. Before we go deeper into designing open channels, it's important that we understand the key terms used in Paes 218:2017. These definitions form the foundation of everything we'll apply in hydraulic analysis and channel design. Let's go through them one by one, along with some practical examples and their real-life applications. First is area, which refers to the cross-sectional area of the flow. It is measured perpendicular to the direction of the water movement. For example, if you slice through a trapezoidal irrigation canal and look at the shape of the flowing water from the side, that visible surface is the flow area. This measurement is essential because it helps determine the flow rate of water moving through the channel. Next is the channel bed slope, which describes how much the bottom of the channel inclines or drops over a certain distance. If a farm ditch lowers by 1 meter over a span of 100 meters, its slope is 1%. This slope influences the speed of the water. Steeper slopes allow water to move faster, which is critical in designing efficient irrigation systems. Depth is the vertical distance from the water surface to the channel bed. For instance, if water in a canal reaches 1.5 meters from the bottom, that's the depth. Knowing this helps engineers make sure the channel can hold enough water without overflowing or underperforming. The energy grade line, also known as the specific energy line, includes both the elevation of the water surface and the velocity head. In real-world applications, this line represents the total energy of flowing water. For example, in high-velocity canals, the energy line may be above the actual water surface due to the speed of the flow. This is useful for evaluating how water behaves under different energy levels. Freeboard refers to the vertical space between the water surface and the top of the channel. If a canal has 0.5 meters of extra height above the water level, that's its freeboard. This added space serves as a buffer to prevent overflow during sudden increases in flow due to rain or irrigation changes. The hydraulic depth is calculated by dividing the flow area by the top width of the water surface. If a flow has an area of 2 square meters and a top width of 1 meter, then the hydraulic depth is 2 meters. This value is especially important when analyzing flow types using parameters like the Froude number. The hydraulic grade line, or hydraulic gradient, traces the free water surface. In uniform flow, this line stays level with the water. Understanding this helps in evaluating the pressure and energy distribution along the canal. Next is hydraulic radius, which is the cross-sectional area of flow divided by the wetted perimeter, the part of the channel wall that comes into contact with water. This value plays a big role in estimating flow velocity using equations like Manning's formula. A line channel is one where the walls and bottom are made of impermeable materials such as concrete. These are common in many irrigation systems because they reduce seepage and prevent erosion. For example, many rice irrigation canals in the Philippines are concrete-lined for better water control and durability. Normal depth refers to the constant depth of flow in a channel under uniform flow conditions. It's the ideal, steady water level that engineers use as a reference for design and analysis. Open channel flow simply means water flow where the top surface is exposed to the atmosphere. Examples include canals, ditches, streams, and even culverts or partially filled pipes. This is the most common type of flow in agricultural water systems. The slope of the hydraulic grade line shows how much the water surface drops along the length of the channel. Similarly, the slope of the energy grade line includes both the slope of the water surface and the energy from flow velocity. These slopes are essential in understanding how energy and water levels change along the channel, especially in non-uniform conditions. Side slope is the ratio between the horizontal and vertical dimensions of the channel wall. For example, a side slope of 2:1 means that for every meter the wall goes up, it stretches 2 meters horizontally. This ratio helps keep the channel stable and prevents collapse, especially in soil-based structures. The top width refers to how wide the water surface is across the channel. For instance, if the water stretches 3 meters from one side to the other at the top, that's the top width. It's an important part of flow and capacity calculations. Uniform flow happens when the depth, area, discharge, and velocity all stay consistent along a portion of the channel. This is the flow condition assumed in most design scenarios because it simplifies analysis and makes performance more predictable. An unlined channel is one that is simply dug through the soil, without concrete or any lining. These are more affordable but prone to seepage and erosion. A common example is a basic farm ditch formed by excavation, where the same soil is used to build the embankments. Finally, the wetted perimeter is the part of the channel boundary that is in contact with the flowing water. In a U-shaped canal, this includes the bottom and the curved walls. It directly affects friction and flow efficiency, and is a key variable in hydraulic equations, design requirements and procedure. And that wraps up the key definitions used in Paes 218:2017. Understanding these terms will make it much easier to follow along in the next parts of the standard where we apply them in actual design. In designing open channels for irrigation systems, whether it's for main canals, laterals, sublaterals, or farm ditches, there are 6 key parameters that need to be determined. These parameters guide us in creating a stable, efficient, and functional channel design. First is design discharge or flow capacity. This refers to the amount of water the channel is intended to carry under design conditions. It's the basis for sizing the entire system. Next is flow velocity. This is the speed at which water travels through the channel. It must be controlled to prevent problems like erosion or sediment buildup. The roughness coefficient represents the resistance to flow caused by the channel's surface. It is essential in computing velocity and discharge using hydraulic formulas. Canal cross-section refers to the shape and dimensions of the channel. The chosen cross-section affects how much water can be conveyed and how stable the channel will be. Bottom slope is the longitudinal slope of the channel bed. It ensures that water flows steadily and uniformly along the length of the channel. Lastly, freeboard is the vertical space between the water surface at design flow and the top edge of the channel. This acts as a safety margin to prevent overflow. All of these design parameters must be considered together to ensure an effective and reliable open channel system. In the following parts, we'll learn how to apply them in actual design computations. For further information, let us discuss one by one based on Paes 218:2017. Design discharge. The design discharge for the main canal shall be equal to the diversion water requirement. Determination of diversion water requirement is shown in PNS/BAFS/Paes 217:2017, Determination of irrigation water requirements. The design discharge for the main farm ditch shall be equal to the farm water requirement. Determination of farm water requirement is shown in PNS/BAFS/Paes 217:2017, Determination of irrigation water requirements. Flow velocity. 5.2.1 For unlined channels, the design flow velocity of the canal shall not exceed the maximum permissible velocity in order to avoid destructive erosion to the channel and progressively destroy fertile lands. The maximum permissible velocity depends on the resistance to erosion of the banks of the canal. The values for different materials are given in Table 1. For lined channels, the minimum permissible velocity shall be considered. However, the flow velocity shall be in no case too low to produce sand deposits or allow weed growth inside the canal. The permissible minimum velocity can be estimated as 0.6 meters per second for plain water and 0.9 meters per second for water with sediments. Table 1 shows the maximum velocities for different types of materials. It includes the type of material and its maximum permissible velocity in meter per seconds. Source: Irrigation Engineering Manual for Diversified Cropping, 1991. Next, roughness coefficient. Use roughness coefficient values based on the long-term surface condition after several years of use, not on the original surface finish. For farm ditches, a roughness coefficient of 0.03 is recommended due to poor maintenance, non-uniform cross-section, common presence of grass or weeds. Table 2 provides roughness coefficient values for various channel materials. Canal cross-section. The recommended shapes for irrigation canals are trapezoidal or rectangular, four-line channels or rock formation, due to their stability and higher resistance to scouring. Thus, the guidelines in this standard are limited to such shapes. Sample cross-section is shown in Figure 3. Cross-sections of other canal shapes are shown in Annex A. Side slope. For lined channels, the recommended side slope is 1.5:1. For unlined channels, side slopes shall depend on soil characteristics and should be flat enough to avoid the possibility of caving in after saturation. Steeper slopes can be permitted in cutting reaches in rock or hard strata but not for embankment reaches. Recommended values are shown in Table 3. Table 3 shows about the stable side slopes for unlined channels. Channel bed width and depth ratio, B/D ratio. For lined and unlined channels, several B/D ratio can be selected in order to satisfy a given design discharge. The bed width and channel depth can be computed by trial and error using Annex B.3. The bed width and channel depth can also be determined by using Table 4, which shows the recommended B/D ratio for a corresponding design discharge. Table 4 shows the recommended B/D ratio. Bottom slope. The bottom slope or the slope of the channel bed shall be determined from the topographic surveys. Freeboard. The flow capacity in the cross-sectional area including the freeboard shall be about 1.25 to 1.35 times the design discharge. For unlined and lined channels, the freeboard shall be calculated based on Annex B.4. The largest value shall be selected for the freeboard. A sample computation is shown in Annex C. Visit the link below for further information about Paes 218:2017. Lastly, canal route selection. The canal route must ensure that design discharge and design depth are maintained. The supply canal should follow the highest points of the land to allow gravity irrigation over the widest possible area. Use appropriate conveyance structures. Example: flumes, siphons. When crossing elevated areas or depressions, avoid high banking or deep-cut sections to maintain efficient water head and velocity. Consider soil conditions, and avoid disruptions to houses and public traffic during canal construction. For long canals serving mainly upland areas, a regulating reservoir is recommended to reduce construction costs and canal size. And take into account existing regional development plans or projects when selecting the canal route. Now that we have known about the design requirements and procedure, it's time to understand how these parameters come together in the actual design process. Each parameter plays a role in determining the size, shape, and performance of the channel. Annex A. This section provides the different cross-sections used in canal design and their corresponding formulas. Each cross-sectional shape has its own set of equations for calculating area, wetted perimeter, hydraulic radius, top width, and hydraulic depth. These are essential for determining the flow capacity and stability of the canal. Understanding these shapes helps engineers choose the most appropriate design based on site conditions, available materials, and desired performance. Annex B. This section provides the general formulas used in open channel design, which include important hydraulic parameters such as hydraulic depth, hydraulic radius, bed width and channel depth, and freeboard. These formulas help us analyze and size the channel correctly to ensure stable, efficient flow. The hydraulic depth is calculated by dividing the flow area by the top width of the water surface. It tells us how deep the flow is, on average, across the channel width. The hydraulic radius is the ratio of the flow area to the wetted perimeter. It's a key factor in determining flow velocity and efficiency using Manning's equation. We also use formulas to solve for the bed width and channel depth based on the desired discharge and side slope. These dimensions define the physical shape of the canal. Lastly, freeboard is determined as an additional vertical distance above the design water level. This ensures safety by preventing overflow during sudden changes in flow or water level. These general formulas are foundational to any open channel design, and mastering them is essential for accurate and effective engineering work. And that wraps up our discussion on the key design concepts and formulas for open channels based on Paes 218:2017. Understanding these fundamentals is essential for designing efficient and reliable irrigation systems that support agricultural productivity. If you found this video helpful, don't forget to like, subscribe, and share it with fellow students and professionals in the field of agricultural and biosystems engineering. For more tutorials, standards breakdowns, and engineering topics, stay tuned to AB Engineering Guild, where we make technical concepts simple and practical. Thanks for watching, and see you in the next video.